Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes, que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Every morning, as the sun creeps over the horizon, a silent, high-stakes computation begins in your backyard. We often think of plants as passive solar panels, simply absorbing light to make sugar. But if a leaf were just a simple collector, it would burn to a crisp within minutes of high noon exposure. To survive, plants have evolved what physicists call the photosynthetic transistor. It's a biological mechanism that performs quantum logic at room temperature, something our most advanced supercomputers still struggle to do. When a photon hits a leaf, it kicks an electron into a higher energy state, creating what's known as an exciton. This exciton needs to reach the reaction center to trigger the chemical process of photosynthesis. However, the path through the dense forest of light-harvesting proteins is a labyrinth. In classical physics, this energy would bounce around randomly, losing energy at every turn. By the time it reached the center, it would be too weak to do anything, or worse, it would get stuck and create singlet oxygen, a toxic form of oxygen that tears the cell apart from the inside. This is the plant version of a lethal sunburn, known as phototoxicity. To prevent this, the leaf must act like a computer, processing the incoming energy with near-perfect efficiency. Here is where the quantum magic happens. Instead of taking one path, the exciton exploits a phenomenon called quantum coherence. It essentially behaves like a wave, traveling through all possible routes through the protein complex simultaneously. It is performing a search algorithm, much like Grover's algorithm in quantum computing, to find the most efficient path to the reaction center with nearly 100% efficiency. But the truly mind-blowing part isn't just the speed, it's the regulation. A leaf cannot just stay in high-efficiency mode all day. If the sun becomes too intense, the sheer volume of excitons would overwhelm the reaction center, leading to a catastrophic system failure. Imagine a transistor in your phone. It's a switch that controls the flow of electricity by toggling between on and off states. A leaf has a molecular version of this. When the sun is too intense, the leaf realizes it has more energy than it can handle. In response, it performs a biological logic operation. It changes the physical shape and acidity of its light-harvesting proteins, specifically the LHCII complex. This physical shift acts like a quantum switch, diverting the excess energy away from the reaction center and transforming it into harmless heat. This process is called non-photochemical quenching, or NPQ. It is, in every sense of the word, a transistor that manages the flow of quantum information to protect the organism. For decades, scientists thought quantum effects could only happen in ultra-cold laboratories near absolute zero. They believed that the messy, warm, and vibrating environment of a living cell would cause decoherence, breaking the quantum state immediately. However, research into the Fenner-Matthews-Olsen (FMO) complex has shown that plants have built-in dampening systems, molecular vibrations that actually sustain the quantum beat, rather than destroying it. They use the noise of life to keep the quantum logic running. Instead of fighting the environment, the leaf's structure uses the natural jitter of molecules to push the exciton along its path. This discovery has turned the field of quantum biology on its head. By using two-dimensional electronic spectroscopy, researchers have actually seen these quantum beats in action. They watched as the energy waves interfered with each other, proving that the leaf was maintaining a state of coherence for far longer than classical physics would predict. This isn't just a cool biology fact, it's the future of human technology. By studying how a blade of grass manages quantum states at 90 degrees Fahrenheit, engineers are looking for ways to build better solar cells and more stable quantum computers that don't require massive liquid nitrogen cooling systems. We are literally walking on the most advanced technology in the known universe every time we step on a lawn. The next time you look at a tree in the blistering summer sun, don't just see a plant. See a master of quantum engineering, a living circuit board that has been perfecting the art of light management for 3 billion years. It is calculating, switching, and protecting itself with a level of sophistication that we are only just beginning to decode. Nature didn't just invent life. It mastered the subatomic world to ensure that life could thrive under the most powerful energy source in our solar system. For more incredible facts like this, don't forget to subscribe and turn on notifications.